and I'll be able to. All right, so welcome. This will wrap up section 8.1. This is part 2. I took care of part 1 last night. Tonight I'm going to focus on what it really means to take a look at a test of hypothesis. There's a number of components, but they are actually fairly easy to work with, at least I think so. The biggest challenge, honestly, is up front with the translation. And then after that, I suppose, is picking the correct statistical tool. But your calculator is very, very capable of doing wonderful work in this particular section. And that's the way we're going to go. We take a little bit of a winding road to get there, but we will get there, and we'll start right now. All right, anytime we have a test of hypothesis, there are some basic features that we like to try to take care of as we approach the problem. We want to read and identify that claim, and this is really the big challenge that many of my students face, is correctly identifying the claim. That will enable us to write both the null and the alternative hypothesis. Then we'll select a significance level, and I'll remind people of some of the notation in just a moment. And then once we've done that, we can identify or calculate that test statistic. And this test statistic is how we determine what to do with our particular test. So I'll remind people that H naught is the null hypothesis. And it's always written with an equals, although it may be correctly translated as less than or equal to, greater than or equal to, or just plain old equal to. And we always write it with just an equal. It's a little bit of a weird convention, but that's the way we roll. The alternative hypothesis is always written with some form of an inequality. That means a less than, a greater than, or a not equal to. And this rule just never varies. It's always the same. There's a number of times I ask my students during quizzes and exams about what is contained in a null and alternative hypothesis regarding these equalities and inequalities. So you really want to be clear on this. If we go back to the court case analogy that I've worked on over the last couple of videos, the null hypothesis is like the not guilty, and the alternative hypothesis is very much like the guilty. We start out with not guilty, evidence accrues, and if enough evidence is piled up, we'll dispense with the null hypothesis and go with the alternative hypothesis as being most likely to be correct. Now, there are two methods of going about conducting this test of hypothesis. The first method is called the critical value method. And I always start with this because it's very, very, very visual. And I've already mentioned it once or twice. With the critical values method, what we do is we use the null and the alternative hypothesis to identify these rejection regions. This is set by that level of significance, alpha. Then what I do is I plot my test statistic relative to those rejection regions. And this makes it possible for me to determine an outcome, and then I can address whatever the initial claim was. The rejection region means that my data, in terms of the central limit theorem focus, is far enough away from the null hypothesis, somewhere right around there, that I really have to consider the null hypothesis as most likely incorrect. And that's really the way that that comes down. It's a very, very visual method. We have all the tools pretty much that we need. I just need to show you one, the one that we'll use to find the test statistic, and I'll go through a couple of examples of that in a moment. Once that happens, depending on where my test statistic falls, I can go ahead and determine my outcome. I may keep the null hypothesis if the data doesn't differ too much, or I may dispense with the null hypothesis and assume the alternative is most likely true if the data differs significantly. So that's the critical value method, and it's what I start with, but it's really not the method that I or anyone who does statistics uses on a regular basis. There's a second method, and the second method is called the p-value method. And now the p-value method is not as visual, although there's a real visual connection, and I'll make that clear at the appropriate time. But the p-value method allows us to essentially use just the test statistic. And if we go ahead and we plot just that test statistic, I can use my null and alternative hypothesis to determine what might be a value that would be extreme or significantly different from my assumed value in the null hypothesis. And once I have this information in hand, I can determine an area. And I'll remind people that by area, I mean a probability. And I can make a very direct comparison between the level of significance alpha and this probability. And this probability is what we call the p-value. That's what the probability is known as. And it is truly used as the conventional way to conduct a test of hypothesis. As I say, it is a little bit less visual than the critical value method, but your calculator makes it very, very easy to obtain everything you need to do. Your big challenge is making the correct comparison with the p-value method, which is one of the reasons I stress inequalities so much, because it turns out to be quite important. So let me just give you an example of what it means to find a test statistic. Now, there's a couple of examples in your text, and there's some in section 8.1. I focus mostly on the test statistics for the mean and the population proportion, but there's also one for standard deviation, but they all work about the same. So a test statistic is based on two things. It's based on sample data and a claim pulled from that null hypothesis. That is the assumed claim. So we're essentially comparing our data to an assumed value, and we're seeing if the difference is different enough. So here's our claim. 58% of local residents work in another county. So the first thing I want to do is identify the type of claim. The claim involves a percent, or actually a proportion. So this is a claim about a population proportion P. And the claim is that 58% work in another country. So my claim translates to P for population proportion equals 58%, or perhaps 0.58. And that is what we'll actually need to make sure we can go ahead and calculate our test statistic. Now I've got to compare this to my sample data. That's my sample proportion, my p hat. That's the x over n, or the 240 over 400. 240 over 400 if I take a look at that, I believe that is about 60%, give or take 60%, 0.6. I'll need the decimal form, not the percentage form. Now, the other thing I want to do is to write the null and the alternative hypothesis, just to make sure I understand how this is going to work. P equals 58%. And if you go back and look at my example, I believe it was from last night, the inequality that is the flip side of equals is not equals. Now, it's important to make sure we understand that once I've got this, I can also find a claimed Q. That would be 42% or 0.42. Remember, P and Q have to add to 1. So once I've got that in front of me, I'm ready to go ahead and work my calculation. So let me get a fresh piece of paper here. Now that test statistic formula is a play on the central limit theorem when we're working with a proportion. We'll look at the mean in a little bit. So the test statistic for a proportion, z equals p hat minus p divided by, downstairs we got the square root of p hat q hat all over n. And as I pointed out the other day, the p hat and the n come to us from our sample data, while the p and the q come to us from our null hypothesis. So now I can plug in the detail here. Downstairs in the root, we got that 0.58 times 0.42, all divided by the n of 400. I usually take 3 decimal places here. Let me jump over to my calculator and we'll run through this calculation. While it looks intimidating, it actually it's actually very easy to take care of on your calculator without too much issue. So anytime I've got a fraction like this, I go ahead and I take care of my numerator first. So there's a 0.6 minus 0.58. There's a 0.02. I'll divide that by, and now I can pick up my square root function. And the order of operations is literally just 0.58 times 0.42 divided by 100. I don't have to worry about that order of operations. So I'll plug that in, divide that out, and I get a 0.405. And that is my test statistic. Yeah, 0.405. If I round to 3 decimal places. And that's the value I would then plot relative to a rejection region for a test that, in this case, if you take a look at the lecture from last night, I would have what we would call a two-tailed test, and I would plot that test statistic relative to those values. And depending on where that test statistic landed, I would take either the null or the alternative hypothesis as most likely. And my calculator, I mean, you're going to see me find that test statistic once or twice in a couple of different situations. But in general, the calculator really does a very good job of finding me the test statistic. And I'll show you how to do that in just a bit here. Now I want to switch gears to that secondary method of testing a hypothesis. This is the notion of the p-value approach. And a little bit about what I'm going to do here first. Students usually really struggle with the p-value concept about actually where it comes from. Fortunately, it's easy enough to use. So it's kind of like, I can drive my car to work, but and I can even tell you kind of how like, the engine works, right? Gas and air go in and there's a bang and whatnot. But I don't have to really be able to build an engine to drive a car. And it's sort of the same here. So you'll encounter the p-value. You'll have to do two things with it. You'll have to, on occasion, make a calculation and find it. That's a difficult thing on depending on how you take the material. The other thing you'll need to do is to use the p-value process for every hypothesis test for the most part after an initial introduction. It is truly the way to go about doing it, and it's really not that difficult. So when we go ahead and try to find a p-value, and by the way, this is a completely different p than the population proportion or the sample proportion. This is a capital P. I know it's hard to tell. But I'm serious. It is truly a different P. And in the literature, it's very easy to identify the P value. Maybe I can dig something up online and that I can share that'll make a point. But you need both the null and the alternative hypothesis. Well, actually, you need the alternative hypothesis because you need the tail of the test. Thing is, if you get one, you get the other. So, but the alternative hypothesis will tell you the tail of the test. It might be a one-tailed test or a two-tailed test. If it's a one-tailed test, it could be left or right tailed test. If it's a two-tailed test, it's very much like that picture I just drew a little bit ago. So you need that hypothesis. You also need the actual test statistic, kind of like that thing I just calculated. You need that number before I can ask you for a p-value. So I'm going to run through an example or two here, and hopefully you'll see that it isn't really all that difficult to see where it comes from, and you've actually used the keystrokes before. So having said that, my claim here is that my population proportion is equal to 60%. My alternative hypothesis is that P is greater than 60%. Don't worry about where this came from. It's my simple example. And again, I say I want the alternative because I'm interested in that particular alternative hypothesis. I need to determine the type of test, left tail, right tail, or two tail. Then I'll need to plot my test statistic on a distribution, the Z distribution, and then we can go from there. So we have P is greater than 60%. This is a right tail test. And we use the Z distribution because we've got a Z equals. So I've drawn my Z distribution and I've plotted my test statistic. I'm not trying to draw an accurate, graph in the algebra sense. I'm trying to identify the p-value, and that little bit of area there is the p-value. It's the probability of getting a value at least as extreme as the test statistic. at least as extreme as the test statistic. That's the p-value. It's a wordy little thing, and I understand it takes students a while, honestly, to get to a place where they're comfortable with that understanding. Now, having said all of that, I want to point out that we've got a z distribution, and I'm looking for an area or a probability. So I'll want to use my normal CDF tool to find that. So let me jump over to Mr. Calculator, and we'll take care of this, and we'll find the p-value. See, as I said, we've used this set of keystrokes before. It's the z distribution. There's normal CDF. The lower bound is 1.87. The upper bound, 10 raised to the 9th, or something equally ridiculously large. We have the mean and the standard deviation for the z distribution. We'll paste him in. There he is. 0.03074. It's a probability, so I'll take 3 significant digits, not decimal places, digits. So there's the first non-zero, 1, 2, 3. The 4 means 7 stays 7. So 0.0307. So, as I say, the p-value, 0.0307. That's that little bit of area right up in there. So, that's how we find a p-value. It's really pretty straightforward. It's a question that could have been asked way back in 6.1. That's where we learn these sets of keystrokes. Now, there is a bit of a twist. First, if I had had a left tail test, that would have been pretty straightforward. My test statistic would have been over here, and my p-value would have been over here for a alternative hypothesis that was left tail. I had a right tail test here, so that didn't even enter into the picture. Same idea, it just would have been flippy-flopped across 0. However, it is a bit different when we've got a two-tailed test. All right, so here's my claim. P equals 75%. P is not equal to 75%. This is what gives me a two-tailed test. So as I say, you need the alternative hypothesis. In this case, it's two-tail. And I've got a test statistic, just like I had previously. You'll notice that this test statistic is a negative 2.15. Now, because I've got a two-tail test, the area I consider is not just that area, it's also this area too. So I have to extrapolate and double up on my area. So I'll have to take that area 1 and that area 2, and my p-value equals the sum of those two areas. Now, it's a symmetric graph. So really what I just need to do is to take that first area and multiply it by 2. And that'll find me my p-value because of the symmetry of the graph. So let me go ahead and do that. That's a capital P equals. So let me come back over to my other calculator, or my other seat for the calculator. And Here we go. So, second distribution, find normal CDF. And this time the lower limit is a negative 10 raised to the 9th. The upper bound is the negative 2.15. There he is. Now, what do I need to do with that value? You think I just go ahead and multiply it by 2? Yeah. So 0.0315 and change. So again, 3 significant digits, 3155. So this 5 becomes a 6, 0.0316. So my p-value, 0.0316. Remember, it's the sum of these two areas. That's a lot of color. So, p-values. Your calculator finds this when it does a hypothesis test. I occasionally ask you to do this on your own. And it's really not that difficult once you've done it once or twice. But until you've done it, it's a little bit intimidating. Now, the reason we do all of those, the plotting of the test statistic in the critical regions, or the comparison of the p-value to our level of significance, the outcomes are what we want to take a look at right now. So if I'm looking at the critical value method, I believe I said this last night, but I want to make it even more precise, I suppose. If that test statistic falls in the rejection region, it's got to fall there in that rejection region. Maybe there's 2, depending on the test. Then we reject the null hypothesis. If it does not fall in the rejection region, the wording here is important. I mentioned that the other night, and I'm mentioning it again. We fail to reject the null hypothesis. It is not accept. And I understand that this is a bit of a WTF sort of thing. Aren't they the same? And quite honestly, they are not the same. So, as I pointed out last night, it's always possible new evidence could be uncovered and you could redo the test. Now, that was the critical value method, the rejection region method. The p-value method. This is the one that we will use most of the time after an initial look at the other method there, p-value method. So, as I say, this is a simple comparison, and one of my goals will be to explain exactly why the simple comparison works, but I need an example or two in front of me, and hopefully we'll get there before we're done tonight. So the p-value method, if the p-value is less than or equal to alpha, remember alpha? That is that level of significance. Significance, can't quite get it in there. Very common levels of alpha, by the way, are 0.01, 0.05, and 0.10. Although others, on occasion, make a guest appearance. If my p-value here is less than my alpha, whatever it might be, we reject the null hypothesis. On the other hand, if the p-value is greater than alpha, we fail to reject the null hypothesis. You're finding exactly the same thing that you find in the other method in a slightly different fashion, but it's exactly the same information. It's entirely equivalent. And it's just neater and cleaner to do with the p-value method, so all big boys and girls use the p-value method. All right. So there's a couple of other things in 8.1. Some of them I've touched on, the notion of error. I'm going to ask you to take a look at last night's lecture for that. And then it talks about the power of a test. We really do not do anything at all with that. You'll never get a question from me on the quote unquote power of the test. All right, I'm going to stop my recording because I'm done with section 8.1.